The cosmos is a place of silent, violent creation. Its most destructive explosions are also its most essential forces. We are about to journey through 30 staggering facts about supernovas and gamma-ray bursts, the universe's ultimate fireworks. You will discover how these cataclysms forge the very atoms that make up your body, and how a single flash in the depths of space could rewrite life on Earth. We will uncover how ancient astronomers saw stars vanish and how a dying star in our own sky could outshine the moon. What hidden connection do you feel to these distant celestial detonations? Our own sun, a brilliant ball of plasma that dictates our days and warms our world, is a cosmic lightweight. Its most violent tantrums, the solar flares that disrupt our satellites and paint our skies with auroras, are mere sparks compared to the true infernos raging across the cosmos. To understand the scale of a supernova, you must first forget everything you know about stellar power. A single one of these stellar deaths does not just outshine a star. It can, for several incredible weeks, outshine the combined light of every single star in its entire host galaxy. That is hundreds of billions of suns, all outshone by one cataclysm. The energy released in that initial, violent flash is almost beyond human comprehension. In just a few moments, a dying star unleashes more energy than our own sun will manage across its entire 10 billion-year lifespan, from its fiery birth to its quiet demise as a cooling ember. Our star is a tiny, steady candle. A supernova is the entire concept of fire unleashed. That staggering release of energy does far more than create a fleeting cosmic spectacle. It is the universe's ultimate forge. Every single atom of gold in a wedding ring, every particle of silver in a piece of jewelry, and the very iron that carries oxygen in your blood was born in a cataclysm like this. Deep within a stable star, nuclear fusion creates lighter elements like helium and carbon. But this process hits a wall at iron. Creating anything heavier requires a tremendous surge of energy, an input of power so immense that only one event in the cosmos can provide it. When a massive star goes supernova, the explosion's shockwave, with its unimaginable heat and pressure, acts like a cosmic smelter. It bombards atomic nuclei, forcing them to fuse into heavier and heavier elements. In that chaotic billion-degree inferno, the universe forges the elements that are essential for planets, for oceans, and for life itself. The uranium that powers nuclear reactors, the iodine essential for your thyroid, even the calcium in your bones, all were seeded into the cosmos by the violent death of a star that lived and died long before our sun even ignited. So the next time you take a deep breath, consider this. The oxygen you are inhaling was once blasted across space in a stellar explosion of unimaginable fury. We are not just observers of these distant events, we are literally made from their remnants. This cosmic forge operates through two very different, yet equally spectacular processes. The universe has two primary recipes for stellar destruction, each with its own distinct trigger and outcome. The first is known as a Type 1, a supernova. This begins not with a single massive star, but with a stellar corpse called a white dwarf. A white dwarf is the incredibly dense, Earth-sized core of a star like our Sun, left to cool after its nuclear fuel is spent. It is made mostly of carbon and oxygen, and it is held up against its own gravity by a strange quantum effect. But if this white dwarf has a companion star, it can begin to steal material from its neighbor. Think of it like a pressure cooker. As the white dwarf siphons more and more matter, its internal pressure and temperature skyrocket. Eventually, it crosses a critical threshold, reigniting nuclear fusion in a runaway chain reaction. The entire star is consumed in a titanic thermonuclear blast, completely obliterated in an instant. There is no remnant left behind, only an expanding cloud of newly forged elements, rich with iron and silicon. The second type is the core collapse supernova. This is the fate of true stellar giants, stars at least 8 times more massive than our Sun. Their lives are a constant, furious battle, with nuclear fusion in the core pushing outward against the immense weight of the star's own layers pushing inward. This balance holds for millions of years until the star finally produces iron in its core. Iron is fusion's ash. It cannot be fused to release more energy. So the outward push from the core suddenly stops. The result is like a skyscraper whose central support pillar instantly vanishes. The star's outer layers, weighing billions of tons, come crashing down at nearly a quarter the speed of light. This catastrophic collapse rebounds in a fraction of a second, creating a shock wave of unimaginable force that blasts the star's outer layers into space. What remains is either an ultra-dense neutron star or, for the most massive stars, a gravitational pit so deep not even light can escape, a black hole. One is a stellar pressure cooker that detonates, the other is a stellar building that collapses and then explodes outward. Both, however, share one crucial purpose: scattering the seeds of future worlds and life across the galaxy. That remnant, the expanding cloud of a star's death, is not just a theoretical concept. We have a stunningly beautiful example right in our cosmic backyard. In the year 1054, a new star blazed into existence in the constellation of Taurus. Chinese court astronomers, meticulous record keepers of the heavens, documented a guest star so brilliant it was visible in broad daylight for 23 days. It shone in the night sky for nearly 2 years before finally fading from view. Arab astronomers also recorded this celestial visitor, a star where none had been before. They were witnessing a supernova, the violent death of a star some 6,500 light-years away. Today, we know the result of that ancient cataclysm as the Crab Nebula. This magnificent, swirling cloud of gas and dust is the expanding debris from that very explosion, a cosmic crime scene we can still observe almost 1,000 years later. It is essentially a supernova baby picture, a snapshot of the chaotic aftermath frozen in time and still evolving. But the Crab Nebula is far more than a simple cloud. At its very heart lies the crushed core of that long-dead star, a neutron star spinning at an unbelievable rate. This particular neutron star is a pulsar, and it rotates 30 times every single second. Think about that for a moment. An object with more mass than our entire Sun, compressed into a sphere the size of a city, is spinning so fast it could complete hundreds of rotations in the time it takes you to read this sentence. This dizzying spin, combined with an intense magnetic field, acts like a cosmic lighthouse, beaming out powerful pulses of radiation that sweep across the universe with every rotation. This makes the Crab Nebula a living laboratory. By studying it, we can watch how a supernova remnant expands, how it interacts with the surrounding space, and how a pulsar's fierce energy continues to illuminate the cloud from within. It is a direct, ongoing link to an event witnessed by ancient astronomers, proving that the universe's most energetic explosions are not just history, they are an active, shaping force in our galaxy. That pulsar at the heart of the Crab Nebula is a relentless engine, but the true, lasting impact of a supernova lies in the expanding shell of debris itself. This is the supernova remnant, a shock wave of unimaginable force hurtling outwards from the epicenter of the blast. For thousands of years, this wall of energy and matter travels through the cold, dark vastness of interstellar space. It acts like a cosmic snowplow, pushing into the sparse clouds of gas and dust that drift between the stars. This isn't a gentle nudge. The shockwave compresses this diffuse material with immense pressure, squeezing it into dense, tight knots. Within these newly formed, swirling pockets of gas, gravity finally gets a foothold. The compressed material begins to collapse under its own weight, its core heating up until nuclear fusion ignites and a new star is born. This is the profound cosmic cycle. The violent death of one star through the sheer force of its final breath creates the nurseries for countless new suns to flicker into existence. The most energetic explosions in the universe are not merely endings. They are the essential rhythmic heartbeat of galactic renewal, the midwives for the next generation of stars and perhaps the planetary systems that may orbit them. Yet even the awesome power of a supernova can be dwarfed. There exists a phenomenon so brief and so violent that it makes a stellar explosion seem almost gentle. Gamma-ray bursts are the single most energetic events we have ever detected in the universe, second only to the Big Bang itself. In a flash lasting mere seconds, one of these cosmic blasts can unleash more energy than our Sun will produce across its entire 10 billion-year lifetime. Think of the Sun's total output from birth to death, compressed into the time it takes you to draw a single breath. That is the staggering, almost nonsensical intensity of a gamma-ray burst. Their light is so brilliant that we can detect them from the very edge of the observable universe. From galaxies so far away, their light has been traveling towards us for billions of years. These are not the deaths of mere stars, they are the universe's ultimate detonations. Scientists classify these fleeting cosmic infernos into two distinct categories, a split based on the duration of their brilliant flash. We call them long and short gamma-ray bursts. The long bursts are the true marathoners of annihilation, their furious gamma-ray emission lasting more than 2 seconds and sometimes stretching for several minutes. This extended fury is the signature of a very specific and spectacular stellar death. A long gamma-ray burst is the final, piercing scream of a star dozens of times more massive than our Sun. When such a behemoth exhausts its fuel, its core does not just collapse into a neutron star. It falls inward with such unstoppable force that it creates a newborn black hole almost instantly. As the star's outer layers rain down toward this newborn singularity, they don't just vanish. They form a searingly hot, spinning disk of material around the black hole, a cosmic vortex of doomed matter. From the poles of this system, like twin blowtorches of pure energy, the black hole blasts out jets of particles and radiation at nearly the speed of light. It is these focused, unimaginably powerful jets, beaming directly through what remains of the star, that we observe as a long gamma-ray burst. If you are not in the precise path of that jet, you would see a brilliant supernova. But if you are looking right down the barrel, you witness the universe's most powerful and persistent beam of light. The short gamma-ray bursts are an entirely different kind of violence. These are the sprinters, lasting less than 2 seconds and often for only a few hundred milliseconds. Their origin is not a single dying star, but a catastrophic celestial dance between two of the densest objects in existence, neutron stars. For billions of years, a pair of these stellar corpses can orbit one another, slowly losing energy and spiraling closer together. In the final moments, they plunge toward each other in a final, furious embrace. When they collide, the impact is so violent that it ripples the very fabric of space-time, sending out gravitational waves. It also flings a fraction of their incredibly dense material into space, creating a blazing hot cloud where neutrons are slammed together to form heavy elements like gold and platinum. In the heart of that chaotic merger, a black hole is often born, and for a breathtakingly brief instant, it too can fire off jets of gamma radiation. A long burst is a single star's death cry, announcing the birth of a black hole. A short burst is the final, silent crash of two dead stars, a collision that forges cosmic treasure and, for a single heartbeat, outshines everything else. This terrifying power is not just a distant spectacle. A gamma-ray burst aimed at Earth from within our own galaxy would be an existential threat. The true danger does not lie in the initial flash of gamma rays, which would bathe our atmosphere in radiation. The catastrophe would unfold in the aftermath. That focused beam of energy would fundamentally rip apart the chemistry of our upper atmosphere. breaking apart the molecules of ozone that form our planet's protective shield. This layer is all that stands between life on Earth and the sun's full, unfiltered ultraviolet radiation. With the ozone layer devastated, our planet would be exposed. The resulting flood of UV light would be catastrophic for the base of the food chain. It would devastate phytoplankton in the oceans, which produce a significant portion of our oxygen, and wipe out countless plant species on land. The ecosystem would collapse from the bottom up, leading to a mass extinction event unlike any in recent geological history. We are protected only by the sheer emptiness of space and the unlikely odds of a beam, narrower than a laser pointer from thousands of light years away, being pointed directly at us. Our existence is a fragile balance, one that could be rewritten in an instant by a cosmic event we would see only as a brilliant and final flash in the sky. The most distant gamma-ray bursts are not just distant in space but in time. Their light has been traveling for over 13 billion years, a journey that began when the cosmos was a fraction of its current age. We are witnessing the explosive deaths of the very first generations of stars, events that unfolded in a universe still raw and unformed. These brilliant flashes act as cosmic lighthouses, their beams piercing through the primordial fog that once filled space. By analyzing the subtle fingerprints left on this ancient light as it passes through early clouds of gas, astronomers can decode the composition of the infant universe. They can determine what elements were present or absent in those first few billion years after the Big Bang. Each burst is a time capsule, a fleeting message from an era when galaxies were just beginning to coalesce from the darkness. The sheer power of these explosions allows them to serve as probes for the most remote and ancient corners of existence, revealing conditions we could never hope to see with ordinary telescopes. Every time one of these cosmic alarms goes off from the edge of the known universe, it is not just announcing a stellar catastrophe. It is illuminating the deepest chapters of our cosmic history, offering a glimpse into the violent, chaotic nursery from which all modern structures, including our own galaxy, eventually emerged. The universe saves its most spectacular finales for its true giants. Beyond the familiar supernova lies a far more extreme class of stellar death, a hypernova. This is a core collapse supernova on steroids, the ultimate end for stars so colossal they dwarf our own sun by 50 times or more. Their death is not a graceful fading, but a cataclysm of almost incomprehensible violence, a total self-annihilation that powers the long gamma-ray bursts we detect from across the cosmos. When a star of this immense size exhausts its nuclear fuel, its core does not simply collapse. It fails utterly, with the entire central structure of the star plummeting inward to form a black hole in one swift, decisive moment. This is not a collapse followed by a rebound. It is a direct, rapid descent into a singularity, and the energy released in that plunge is what makes a hypernova so uniquely terrifying and powerful. The infalling matter doesn't just vanish. It forms a frantic, superheated accretion disk around the newborn black hole, a whirlpool of stellar material spinning at nearly the speed of light. It is from the polar regions of this chaotic system that the hypernova unleashes its true fury, focusing its energy into two narrow, opposing jets that blast their way out through the star's outer layers. These jets, composed of radiation and atomic particles traveling at over 99.9% the speed of light, are the particle accelerators of the gods. If our planet were, by some cosmic misfortune, to be aligned with one of these beams from a nearby hypernova, the jet would deliver more energy in a few seconds than the sun has emitted in its entire multi-billion-year history. This is the engine behind the long gamma-ray burst, a stellar death scream so focused and potent it can be seen clear across the observable universe. A hypernova is not just a star dying. It is a star being utterly dismantled, its very being converted into the most focused beam of energy the cosmos can produce. The theoretical power of a hypernova became a stunning reality in October of 2022. On the 9th day of that month, a wave of high-energy radiation swept through our solar system, triggering detectors on spacecraft orbiting Earth. At first, it seemed like a sensor malfunction. The signal was so intense it completely overwhelmed most gamma-ray telescopes, leaving them temporarily blinded by the sheer volume of energy. This was JRB 221009A, an event astronomers would soon nickname the BOAT, the brightest of all time. For over 10 minutes, this single gamma-ray burst delivered more energy to our instruments than any cosmic event in recorded history. Its afterglow, the fading echo of the cataclysm, was so luminous that even amateur astronomers with modest telescopes could observe it for days. This was not a distant, theoretical flash. It was a cosmic monster roaring from a galaxy nearly 2 billion light-years away, and its light was still powerful enough to dominate the high-energy sky. Major observatories around the world and in space immediately swung into action, turning their eyes toward this unprecedented event. They studied its afterglow across the entire electromagnetic spectrum, from radio waves to visible light and all the way up to the highest energy gamma rays. This collaborative effort gave us a complete picture of the explosion's aftermath, a detailed forensic analysis of a stellar death of almost unimaginable scale. The data revealed a hypernova of exceptional power, likely the birth cry of a new black hole from a star dozens of times more massive than our Sun. The BOAT was a stark reminder that the universe is capable of violence on a scale that defies our everyday understanding, and that such colossal events are not just relics of the deep past, but are happening right now in the cosmic darkness. But the collision of two neutron stars does far more than trigger a fleeting flash of gamma rays. It unleashes a different kind of explosion entirely, one that paints the cosmos with a brief, beautiful, and incredibly valuable glow. This is a kilonova. The name itself hints at its power, an event 1,000 times brighter than a typical nova. For about a week, this cosmic forge radiates a brilliant, hot light, often with a distinctive reddish hue as the expanding cloud of newly created elements cools. The true magic of a kilonova happens in the chaos of that collision. As the two incredibly dense neutron stars spiral into each other and rip apart, they fling a staggering amount of their material into space. This is not just any material, it is a soup of neutrons, the building blocks of atomic nuclei. In this neutron-rich environment, a frantic process called rapid neutron capture, or the R process, takes place. Atomic nuclei are bombarded by a flood of free neutrons, allowing them to grow into heavier and heavier elements in a matter of seconds. This is how the universe forges the most precious of its treasures. Nearly all of the gold and platinum in the cosmos, every single atom, is born not in the heart of a supernova, but in the violent merger of two neutron stars. The very gold in a wedding band or a museum artifact was once part of a city-sized stellar corpse, flung into the void during a cataclysm of unimaginable force. These kilonovas are the universe's ultimate gold factories, literally sprinkling newly minted precious metals across galaxies, where they will one day be incorporated into new stars, planets, and perhaps into the history of life itself. This predictable brilliance makes a Type 1 a supernova far more than a cosmic spectacle. It becomes a fundamental tool for mapping the cosmos. Astronomers call them standard candles, celestial lighthouses of known brightness. The logic is beautifully simple. If you know exactly how bright a light source truly is, you can calculate its distance by measuring how dim it appears from your vantage point. A 100-watt light bulb looks much dimmer from a mile away than it does from a few feet. Because every Type 1 a supernova ignites at the same critical mass, they all reach roughly the same peak intrinsic brightness. When astronomers spot one of these stellar explosions in a distant galaxy, they know its true luminosity instantly. By carefully measuring how faint it looks to us here on Earth, they can calculate the distance to its host galaxy with incredible precision. This method unlocked one of the most profound discoveries of the 20th century. Two independent teams of scientists were using these supernova standard candles to measure the expansion rate of the universe, expecting to find that the pull of gravity was slowing it down. Instead, they found the opposite. The most distant supernovas were fainter than their redshifts suggested they should be. They were farther away than anyone had predicted. The inescapable conclusion was staggering. The expansion of the universe is not slowing down. It is speeding up. Some mysterious, repulsive force, which we now call dark energy, is overpowering gravity and pushing galaxies apart at an ever-increasing rate. This discovery, which earned the Nobel Prize in Physics in 2011, hinged entirely on the reliable, predictable flash of a dying white dwarf star. A stellar death billions of light-years away revealed a fundamental secret of cosmic structure, proving that the universe is filled with a mysterious energy we are only just beginning to understand. The brilliant flash of a supernova is just the opening chapter of its story. To truly understand the cataclysm, astronomers watch how that light fades, tracing its path on a graph known as a light curve. This simple plot of brightness against time is the ultimate forensic report for a stellar death. Its shape, the speed of its rise, and the slow decay of its fall reveals secrets locked within the explosion itself. Each type of supernova leaves a unique fingerprint on its light curve. A Type 1, a supernova born from a detonating white dwarf, has a remarkably predictable pattern. It climbs to a sharp, brilliant peak and then fades in a very specific, orderly way, which is precisely what makes it such a perfect standard candle for measuring cosmic distances. In contrast, the light curve of a core collapse supernova tells a more complex tale. Its brightness is powered by the radioactive decay of elements forged in the blast, most notably an isotope of nickel. The initial peak is often broader, and the decline is governed by the half-life of that radioactive material, acting like a cosmic clock ticking down within the expanding cloud. By analyzing the exact shape of this curve, scientists can deduce the sheer quantity of nickel-56 created in the explosion, which in turn points to the mass of the original star. A more massive progenitor star will forge more of this radioactive fuel, leading to a brighter and longer-lasting peak. The light curve becomes a direct window into the star's identity, telling us not just how it died, but how it lived. This single graph, a record of fading brilliance, allows us to reconstruct the size, composition, and explosive mechanics of a star we will never see again, turning a point of light in the sky into a detailed postmortem of a cosmic giant. That predictable rhythm of stellar death can sometimes break. While we think of a supernova as a star's final, brilliant performance, some stars skip the show entirely and simply vanish. This is the strange case of the failed supernova. It begins with a true stellar giant, a star at least 20 times more massive than our Sun. According to all our models, such a star is destined for a core collapse supernova, a titanic explosion that scatters its enriched guts across the galaxy. But for some of these behemoths, the final act goes silent. Instead of rebounding in a brilliant shockwave, the star's entire core collapses directly into a black hole. The infalling matter crosses the event horizon with such efficiency that there is no rebound, no explosive shockwave to blast the star's outer layers into space. The outer shell of the star, deprived of its supporting core, simply falls into the newly formed black hole. From our distant vantage point, a star that shone for millions of years would simply wink out of existence, leaving behind an empty patch of sky and a profound mystery. The first strong evidence for this came from a survey searching for normal supernovas. Astronomers were monitoring a giant red star in a distant galaxy, and then one day it was just gone. They scrutinized the spot with the most powerful telescopes available, but the star had vanished without a trace. There was no expanding cloud of gas, no brilliant flash, not even a faint afterglow. It had been there, and then it was not, as if a cosmic magician had pulled away the cloth to reveal nothing underneath. This silent disappearance is the ghostly signature of a failed supernova, a stellar giant that chose to leave the universe with a whisper instead of a bang, collapsing so completely that not even its own light could escape. For stars of truly monstrous size, even a hypernova is not the final word. There exists a theoretical class of stellar death so absolute it makes a black hole seem gentle. These are pair instability supernovas, the universe's ultimate self-destruct mechanism. They are thought to occur in stars of immense proportions, between 140 and 260 times the mass of our Sun. Within the cores of these cosmic giants, temperatures and pressures reach such staggering extremes that a strange and catastrophic process begins. The core is so hot that the photons, the very particles of light carrying the radiation pressure that holds the star up, begin to spontaneously transform. They convert their pure energy into pairs of electrons and their antimatter counterparts, positrons. This transformation, known as pair production, is a disaster for the star's stability. Radiation pressure suddenly plummets like a building's support beams instantly turning to smoke. Without that outward push, the core collapses under its own immense weight. But this is not the orderly collapse that forms a neutron star or a black hole. This implosion is so violent and heats the core to such unbelievable temperatures that runaway nuclear fusion ignites, burning through its remaining fuel in an instant. The entire star does not just explode, it is completely and utterly disassembled in a cataclysm of pure fusion fire. The shockwave is so powerful that it scatters every single atom of the star into the void. There is no remnant left behind, no neutron star, no black hole, not even a wisp of a corpse. The star simply ceases to exist, annihilated in a flash of light that can outshine an entire galaxy of normal stars. This is a stellar death with no grave, a final explosion so thorough that it erases the very evidence of its own existence. That expanding shell of a supernova is more than a cloud of debris. It is a natural engine of incredible power, generating radiation that we can see and invisible particles that saturate the cosmos. The shockwave itself, a wall of energy moving at millions of kilometers per hour, acts as a cosmic particle accelerator on a scale we could never hope to build on Earth. As this magnetic bubble of hot gas plows through space, it traps charged particles like protons and electrons within its turbulent folds. These particles are caught in a magnetic slingshot, bouncing back and forth across the shock front. With each crossing, they gain a tremendous burst of speed, eventually being flung outward at velocities approaching the speed of light. These are cosmic rays, and they are constantly raining down on our planet. Every single second, hundreds of these high-energy particles from distant stellar explosions pass right through your body. They are completely harmless at these levels, a silent, invisible drizzle from the galaxy's most violent events. Without the protective blanket of our atmosphere, this particle rain would be a serious hazard to life. It is the supernova remnant, acting as a natural accelerator, that fills our galaxy with this faint, radioactive whisper, a constant reminder of the energetic forces shaping the universe around us. A supernova is the ultimate silent movie, a brilliant flash in the vacuum of space. Yet scientists have found a way to give these cataclysms a voice. They translate the raw data from these explosions into sound, a process called sonification. Imagine taking the wild, fluctuating curve of a supernova's light, the ebb and flow of its X-ray emissions, and mapping it directly to a pitch. A sudden surge in brightness becomes a piercing high note. A slow decay in gamma rays becomes a deep, rumbling bass. The result is not a melody but a symphony of chaos. You would hear the initial, shattering crescendo of the star's death, a violent peak of sound that mimics the shockwave tearing through space. This would be followed by the churning, turbulent tones of the expanding remnant, a cacophony of magnetic fields twisting and snapping, of elemental gases colliding at unimaginable speeds. It is the sound of cosmic creation and destruction, a sensory experience of a force too grand for our eyes to process alone. Listening to the data makes the invisible turbulence real, transforming abstract numbers into a visceral, roaring storm. Long before the Crab Nebula lit up the skies, another guest star made its mark on human history. In the year 185, during the height of the Han Dynasty, Chinese court astronomers gazed up and saw a brilliant new light in the constellation we now call Circinus. Their meticulous records describe a guest star, an unexpected visitor that shone brightly for 8 months before finally fading from view. It was a celestial mystery, a star that appeared where none had been before and then slowly vanished. For centuries, this ancient observation remained a solitary data point, a curious footnote in the history of stargazing. Then, modern astronomy provided the stunning answer. Using powerful telescopes, scientists identified a vast, expanding shell of gas known as RCW-86. When they traced the motion of this remnant backwards in time, its path led them directly to that same patch of sky documented nearly 2,000 years ago. The calculations were a perfect match. The cloud of RCW-86 is the expanding debris from that very explosion, the ghost of a star that died while the Roman Empire still stood. This creates an incredible bridge across time, connecting the careful observations of ancient scholars with the forensic tools of contemporary astrophysics. We are not just looking at a cloud of gas, we are reading the final chapter of a story that began when astronomers first put brush to silk and recorded a strange new light in the heavens. This direct link proves that the violent cosmos has been performing its grandest spectacles for all of human history, witnessed by curious eyes in every age. This invisible drizzle of high-energy particles is a constant, shaping presence throughout the Milky Way. Supernova remnants do not just forge the atoms of our bodies, they also fill the voids between the stars with a faint, persistent radiation. These cosmic rays are the shrapnel from stellar explosions, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light. They spiral through the galaxy's magnetic fields, creating a pervasive, energetic fog that constitutes a significant part of the natural background radiation in space. Every planet, every moon, every asteroid in our galaxy is bathed in this subtle, radioactive rain. For our own world, protected by its atmosphere and magnetic field, the effect is minimal at the surface. But for astronauts on the International Space Station or future travelers to Mars, this particle bath is a serious occupational hazard, a tangible reminder of the violent galactic environment we inhabit. The influence of these particles, however, may reach far deeper than space travel. When a high-energy cosmic ray, a proton forged in a long-dead star, streaks through our atmosphere, it can create a shower of secondary particles. Some of these can reach the Earth's surface, and on very rare occasions, one can pierce a living cell. If it strikes a DNA molecule just right, it can cause a mutation, a tiny, random change in the genetic code. Most of these mutations are harmless or are repaired by the cell itself. But over millions of years across countless organisms, this steady, low-level bombardment provides a source of genetic variation. It is not the primary driver of evolution, but it acts as one of many cosmic dice rolls, introducing random changes upon which natural selection can act. The death of a distant star, therefore, might have played a subtle, indirect role in the grand tapestry of life on Earth, its final explosive breath contributing to the raw material of biological change. The brilliant light of a supernova is a cosmic lie. It is a beautiful, luminous distraction from the true engine of the explosion. For every single photon of visible light that floods into space, a staggering 99% of the star's total energy escapes in a completely different form, carried by a ghostly tide of neutrinos. These are the universe's most elusive particles, so tiny and nearly massless that they barely interact with anything at all. Trillions of them are passing through your body every second, leaving no trace, as if they were phantoms moving through a solid wall. In the final, catastrophic collapse of a massive star, the core is compressed into an impossibly dense sphere. The protons and electrons there are forced together under such immense pressure that they merge, transforming into neutrons and releasing a vast flood of these neutrino phantoms. In that single, violent second, the dying star emits more neutrinos than there are stars in the entire observable universe. This is the star's true death cry, a silent, invisible scream that carries almost all of its final energy out into the cosmos. We only see the light show because the shockwave has to fight its way through the star's outer layers, but the neutrinos, being ghosts, simply flee directly through the solid matter, announcing the cataclysm to the universe almost instantly. This is why the detection of these particles from a supernova is a landmark event in astronomy. In February of 1987, neutrinos from a star that died in the Large Magellanic Cloud, a nearby dwarf galaxy, washed over our planet. Hours before the light from supernova 1987 reached Earth, underground detectors in Japan and the United States registered a brief, telling burst of 24 neutrinos. This was the direct signal from the collapsing core itself, a message from the heart of the explosion that arrived before the visual fireworks even began. It was the first and only time we have directly witnessed the birth of a neutron star through its ghostly neutrino pulse, confirming a fundamental prediction of stellar physics and giving us a fleeting, direct window into the most violent process a star can endure. These brilliant new stars did not just light up the night sky, they ignited a revolution in human thought. In November of 1572, the Danish nobleman Tycho Brahe gazed up at the constellation Cassiopeia and saw a star where none had been before, shining as brightly as Venus. According to the ancient teachings of Aristotle, which had dominated science for 2,000 years, the heavens beyond the moon were perfect and unchanging. Stars were fixed, eternal, and incorruptible. This new star was a direct and stunning contradiction, a crack in the foundation of the entire cosmic order. Tycho, a meticulous observer, used his instruments to prove it had no measurable parallax, meaning it was not a nearby atmospheric phenomenon, but resided firmly in the realm of the distant stars. It was a change in the immutable heavens, and it could not be ignored. This supernova, now known as Tycho's star, forced European astronomers to confront an undeniable truth. The cosmos was not the static, perfect realm they had been taught. It was a place of dynamic, violent change. Just over 30 years later, in October of 1604, the cosmos delivered another blow. A second supernova, even brighter than Jupiter, appeared in the constellation Ophiuchus. The German astronomer Johannes Kepler, Tycho's former assistant, studied this guest star with intense fascination. He watched it for over a year, meticulously tracking its slow fade from view. Kepler's supernova served as a final, emphatic confirmation. The heavens were not perfect, they were a realm of flux and transformation, just like the Earth. These two stellar explosions, seen by the founders of modern astronomy, shattered the Aristotelian worldview and created an intellectual vacuum. Into that void stepped a new way of thinking, one based on observation, measurement, and mathematical law rather than ancient authority. The path was now clear for the scientific revolution that would follow, a direct line from these dying stars to the laws of planetary motion and a sun-centered solar system. The universe had spoken with the voice of stellar catastrophe, and humanity was finally learning to listen. The death of a distant star might be more than a cosmic spectacle. It could be a force that sculpts the very climate of our world. There exists a provocative scientific hypothesis linking stellar explosions to one of Earth's greatest ice ages. The mechanism involves a supernova occurring dangerously close to our solar system, perhaps within a few hundred light years. Such a nearby cataclysm would not threaten us with gamma rays, but with a sustained downpour of cosmic rays. These high-energy particles, the shrapnel from the explosion, would flood our region of the galaxy for thousands of years. As this invisible rain poured into Earth's upper atmosphere, it would have a direct physical effect. Each cosmic ray can act as a seed, encouraging the formation of tiny water droplets that coalesce into clouds. An increased density of cosmic rays could theoretically lead to a greater global cloud cover, particularly of low-lying clouds that are highly reflective. This is where the climate connection becomes profound. More clouds mean more sunlight is bounced back into space before it can warm the planet's surface. This planetary dimming could initiate a global cooling trend, a slow descent into a glacial period that lasts for millennia. Some researchers point to geological evidence from the Pliocene epoch, around 2.5 million years ago, where layers of ocean sediment show a curious spike in radioactive iron isotopes, a potential fingerprint of a nearby supernova, coinciding with the onset of a major ice age. While this idea remains a compelling theory rather than settled science, it forces a breathtaking perspective. The great ice sheets that once scraped across continents, shaping our very geography, may have had their origins in the silent, ghostly fallout from a stellar catastrophe witnessed by no human eyes. But the dense husk of a neutron star is not the final word in stellar evolution. Some of these stellar corpses are born with a truly terrifying property, a magnetic field of almost unimaginable intensity. We call these objects magnetars. A magnetar is a neutron star, but one that has been twisted into a cosmic monster by the physics of its own violent birth. During the supernova collapse, if the star's core is spinning rapidly and its internal magnetic field is perfectly aligned, that magnetic field can be amplified to an almost nonsensical degree. The result is a magnetic field a quadrillion times more powerful than the one that surrounds our Earth. To grasp that scale, imagine a common refrigerator magnet. Now imagine that same magnetic force, but strong enough to wipe the data from every credit card on the planet from a distance halfway to the moon. This is not a gentle field, it is a form of cosmic stress made manifest. The magnetic field of a magnetar is so ferociously strong that it places the very crust of the neutron star under unbearable strain. This crust is not like rock on Earth. It is an immensely dense crystalline structure, a shell of iron nuclei locked in a rigid lattice. The magnetic field exerts such incredible pressure on this shell that the crust eventually cracks. This event is known as a starquake, and it is one of the most violent releases of energy in the modern universe. When the crust of a magnetar fractures, it unleashes a colossal flare. In a single second, such a flare can release more energy than our sun will emit over 100,000 years. These are not the long, focused beams of a gamma-ray burst, but immense, short-lived eruptions of X-rays and gamma rays that can temporarily outshine every other source in the galaxy. For a brief, blinding moment, a single city-sized object can outshine hundreds of billions of stars, all because its own magnetic power has literally torn its skin apart. Even the most familiar cosmic landmarks can suddenly reveal a new face. The supernova remnant Cassiopeia is one of the most studied objects in the sky, the expanding debris from a star that died around 350 years ago. We thought we understood its structure, a chaotic bubble of ejected gas and dust. Then the James Webb Space Telescope turned its infrared gaze upon it, and a mystery emerged. Nestled within the remnant's intricate shell was something utterly unexpected. A strange, web-like structure of glowing green filaments. Astronomers quickly nicknamed this bizarre feature the Green Monster. It looks like a cosmic cage or perhaps the ghostly outline of a colossal celestial lung. This is not a simple cloud. Its complex, bubbly texture suggests a turbulent history we never knew was there. The Green Monster appears to be a section of the star's own inner material, blasted outward during the explosion, but its exact origin and the forces that shaped it remain a profound puzzle. The very presence of this structure is forcing scientists to rewrite their models of the supernova's final moments. It suggests that the star's death was far more complicated than a simple spherical blast wave. Instead, the explosion seems to have been wildly asymmetrical, with immense frothing bubbles of hot gas erupting from the interior and punching through the outer layers. The green monster is the fossilized imprint of that internal chaos, a relic from deep inside the star that was violently sculpted during its death throes. This single, enigmatic feature proves that the final seconds of a supernova are a turbulent, three-dimensional storm, a reality we are only now beginning to see. A supernova's violence can fling its own corpse across the galaxy. This cosmic ejection happens when a star explodes within a binary system, a pair of stars locked in a mutual gravitational dance. The explosion that creates a neutron star or black hole is rarely a perfect, symmetrical blast. It is a chaotic, lopsided event, with shockwaves and jets of neutrinos erupting more forcefully in one direction than another. Think of firing a rifle. The bullet flies forward, but the gun itself recoils sharply backward into your shoulder. In a supernova, the exploding stellar material is the bullet, and the newborn neutron star is the gun. If the explosion is even slightly imbalanced, the recoil delivers a tremendous kick to the ultra-dense remnant. This kick can launch it out of its home system at speeds exceeding 1,000,000 miles per hour, fast enough to cross the entire United States in less than a single second. Suddenly, the silent, dark corpse of a dead star is transformed into a runaway, a lone wanderer on an endless journey through the galactic void. Astronomers have actually tracked these fugitives. They observe isolated neutron stars, their powerful magnetic fields and radiation creating brilliant wakes, hurtling through clouds of interstellar gas. These are the ghosts of stellar catastrophes, cast out by the very explosions that created them, forever fleeing the scene of their own death. That stellar shrapnel flung into the void does not simply vanish into the emptiness. It drifts for eons, mingling with the cold, dark clouds of gas that float between the stars. This is the cosmic recycling bin, the raw material for everything that comes next. When the shockwave from a new supernova plows into one of these clouds, it triggers the birth of a new stellar generation. But this new star is not a blank slate. It forms from a cloud that has already been seeded with the heavy elements forged in that ancient explosion. The new star, and any planets that coalesce around it, literally inherits the atomic legacy of its long-dead predecessor. This is stellar pollution in its most beautiful form. It is not a stain, but a chemical fingerprint, a story written in the very light the star emits. Astronomers can read this story using a technique called spectroscopy. By breaking a star's light into a rainbow of colors, they can see dark lines at specific wavelengths like a unique barcode. Each line corresponds to a specific element present in the star's outer layers. When they see an overabundance of elements like gold, platinum, or uranium, they know they are looking at a second or third generation star. Its birth cloud was enriched by the cataclysmic death of a much older, more massive star that lived fast and died young. This allows scientists to perform a kind of galactic archaeology, tracing the history of supernova explosions throughout our Milky Way's long history. Our own sun carries this chemical signature, a telltale mix of heavier elements that proves it is a child of the cosmos, born from the ashes of countless stellar giants that perished long before our solar system even began to form. One of those stellar corpses is already in our sky, a ticking time bomb in the familiar shape of Orion. The star Betelgeuse, that fiery red shoulder of the hunter, is a swollen supergiant on the very brink of catastrophe. It is so colossal that if it replaced our sun, its outer surface would extend beyond the orbit of Jupiter, engulfing the inner planets. This immense size is a sign of a star in its final death throes, having burned through its core fuel and now fusing elements in a desperate, unstable dance. Betelgeuse is a prime candidate to end its life in a core collapse supernova, an event that could happen at any moment within the next 100,000 years. In cosmic terms, that is the blink of an eye. When it finally explodes, the spectacle will be unlike anything witnessed in recorded human history. The detonation will not be a faint point of light. For a period of several weeks, it is predicted to shine with the brilliance of a full moon, a second, intense celestial lantern hanging in the constellation of Orion. It would be starkly visible during the day, a dazzling pinprick of light beside the sun, and would dominate the night, casting sharp, distinct shadows on the ground. This would not be a distant astronomical event noted by scientists alone. It would be a global, unavoidable phenomenon, a constant reminder of the violent universe watching us from above. The star that has guided sailors and storytellers for millennia would transform into the sky's most brilliant warning, a final, glorious performance before vanishing from our sky forever. We can witness their final light, but to understand their final moments, we must recreate a star's death from the inside out. This is the monumental challenge of supernova simulation, a task so complex it demands the raw power of the world's most advanced supercomputers. A modern supercomputer, a machine filled with hundreds of thousands of processors working in perfect harmony, will dedicate months of calculation to simulate just a few seconds of a star's catastrophic collapse. The problem is one of unimaginable complexity. You are not modeling a simple sphere of gas. You are attempting to capture the behavior of a trillion-degree nuclear furnace, where the fundamental forces of nature are locked in a desperate, multi-dimensional struggle. Gravity is crushing the core. Neutrinos, trillions of them, are flooding out, some escaping while others get trapped and interact. A nascent shockwave forms, stalls, and must be revived. Every single one of these elements influences all the others in a chaotic, turbulent dance. To get the explosion right, scientists must model all of this physics simultaneously in 3 dimensions. Early, simpler models often failed. The shockwave would form and then simply fizzle out, leaving a quiet collapse into a black hole. It was only when these immense simulations began to fully account for the subtle, churning motions deep inside the collapsing star, the sloshing and swirling of superheated plasma, that a critical discovery was made. This internal turbulence, like a pot of water boiling over, acts as a vital engine. It helps to push the stalled shockwave from behind, giving it the extra energy it needs to finally tear the star apart. These digital laboratories have revealed the fine line between a successful supernova that seeds the galaxy with elements and a failed supernova where a star vanishes into darkness. The ghost in the machine is this delicate balance of forces, a balance we can only find by unleashing a virtual star's death inside a city block-sized computer. This journey through cosmic violence leads to a humbling truth. The calcium that forms the structure of your bones, the oxygen that fills your lungs with every breath, and the iron that carries life-giving energy through your veins were not present at the dawn of the universe. They are immigrants, travelers on an epic journey that began in the heart of a dying star. Every one of these essential atoms was forged in the nuclear furnaces of massive stars and then blasted across the light years by the supernova explosions we have explored. You are not just a passive observer of these distant celestial events. You are a living collection of their remnants, a walking, breathing monument to the universe's most creative destructions. This connection is not merely poetic, it is a fundamental fact of chemistry and physics. The carbon that is the backbone of your DNA, the nitrogen that is a crucial component of your proteins, the phosphorus that helps store your cellular energy, all of these were once searing hot stardust, ejected into the void to one day coalesce into a planet, an ocean, and eventually you. We look up at the night sky and see a void, but in reality, we are looking at our own extended family, a diaspora of elements that share a common origin in stellar cataclysm. We are the universe having become conscious of itself, a way for the cosmos to look back upon its own violent, beautiful, and creative history. These cosmic explosions are the architects of reality itself. From forging the atoms of our bodies to sculpting the grand spiral arms of galaxies, their power is the fundamental force behind cosmic change. They are the crucibles that create, the engines that destroy, and the seeds from which new stars and planets are born. Every time we look up at the starry void, we are witnessing an ongoing story of cataclysm and creation, a cycle fueled by these unimaginable blasts. We are not just living in the universe is living within us. The next time you gaze at the night sky, remember the silent, violent origins of the very stuff you are made of. Let us know in the comments which of these 30 facts about the universe's most energetic explosions left you the most amazed.